Hello students, today I am going to explain communication through the band limited channel. So this is a band limited channel in which we are finding an intersymbol interference, that is ISI. So in this ISI, in all digital systems, the pulses are transmitted from the transmitter to receiver, but channels carrying these pulses never have enough bandwidth required to ensure the preservation of the shape of the pulse. Such channels are called as a band-limited channels. Here, the output of a band-limited channel, when a narrow pulse is applied, its input is shown in the previous slide. And also, the band-limited channel tends to spread the narrow pulses. This produces the secondary lobes as shown in the previous slide, and also the secondary lobes are also called as a ringing tails. This is a pulse transmission. Here the figure shows the energy distribution in the output of a band limited channel. It shows that almost 90% energy is contained in the main lobe, while the bandwidth of the channel is 1 by T, and maximum bit rate supported by the channel is 2B. Next, we have pulse shaping, that is intersymbol interference. Here, the process of residual signals at the receiver output due to other symbols interfering with the required symbols is known as intersymbol interference. Spreading of a pulse beyond its allotted time period will tend to interfere with the adjacent pulses. In this digital transmission, ISI rises due to dispersive nature of a communication channel. In a band-limited PCM channel, the received pulse waveform is distorted and may extend to the next time slot. This may result in error in the determination of received bits. And also, this ISI is an undesirable phenomena that results into degradations in the performance of digital communication systems. Next, this is an intersymbol interference. That is, if the rectangular multilevel pulses are filtered improperly as they pass through a communication systems. They will spread in time, and the pulse for each symbol may be merged into adjacent time slots and cause an intersymbol interference. This is an example of an ISI on received pulse in a binary communication system. Next, we have pulse shaping interference intersymbol. In the absence of ISI and channel noise, the transmitted symbol can be decoded correctly at the receiver. But due to occurrence of ISI, an error will be introduced in the decision-making device at the receiver output. So this is an intersymbol interference. So here we have taken the block diagram here, that is a baseband binary data transmission system. So here first we have taken a transmitter, next we have a channel, next we have a receiver. That is, in the transmitter we have pulse generator, clock pulses, as well as the transmitting filter. Next, in the receiving part we have receiving filter as well as a decision device and the threshold value. So here in this block diagram, the input signal consists of a binary data sequence BK with a bit duration of TB seconds, and then the sequence is applied to a pulse generator producing the discrete PAM signal. And the major source of this system degradation is dispersion in the channel. That is, we assume that the channel is noiseless but dispersive. The channel output is then passed through a receiving filter of transfer function HR of F. This filter output is sampled synchronously with the transmitter, with the sampling instance being determined by a clock or a timing signal that is usually extracted from the receiving filter output. Next, finally, the sequence of the samples thus obtained is used to reconstruct the original data sequence by means of a decision device. That is, each sample is compared to a threshold value, and then we assume that the symbols 0 and 1 are equally likely and the threshold is set halfway between their representation levels. That is, if the threshold is exceeded, a decision is made in favor of symbol 1. Or if on the other hand the threshold is not exceeded, then a decision is made in favor of symbol 0. That is, if the sample value equals the threshold exactly, the flip of a fair coin will determine which symbols was determined. Next, we have a intersymbol interference. So here the receiving filter output, it is given by y of t, and it is given as a mu into summation k equals minus infinity to infinity ak p of t minus a ktb, and the output y of t is produced in response to the binary data waveform applied to the input of the transmitting filter. The pulse mu pt is the response of the cascaded connection of a transmitting filter and the channel of the receiving filter. Here mu into P of f will be equals to V of f into H T of f into H C of f into H R of f. That is the receiving filter output Y of t is sampled at a time t equals I TB. And also the output of Y of t will be equals to mu into summation k equals minus infinity to infinity AK P of ITB minus KTB. So next we have symbol interference. So here the first term in the above equation, the first term is represented by the I, the transmitted bit, and the second term represents the residual effect of all the other transmitted bits on the decoding of the ith bit. This residual effect is called as an ISI, and also this ISI arises because of imperfections in the overall frequency response of the system, and also the frequency components constituting the input pulses are differently attenuated and differentially delayed by the system. Consequently, the pulse is depressed at the output. Next, we have intersymbol interference. In the absence of ISI, that is, in the absence of intersymbol interference, Y of t will be equals to mu into AI. That is, in the design of the transmitting and receiving filters, the objective is to minimize the effect of ISI and thereby deliver the digital data to its destination with the smallest error rate possible. Next, we have Nyquist criteria for distortionless baseband binary transmission. Here, the transfer function of the channel and the transmitter pulse shape are specified. But the problem is that to determine the transfer function of the transmitting and receiving filter, so as to construct the transmitted data sequence BK. Here, the receiver constructs a data sequence BK by extracting and decoding the corresponding sequence of weights from the output, and the extraction involves sampling the output y of t at some time, that is t equals ITB, and the decoding requires that the weighted pulse contribution as shown in equation, that is AKP of ITB minus KTB, to overlap the trails of other weighted contribution by K not equals to I. Next, this is the Nyquist criteria for distortionless baseband binary transmission. Here, this requires that it is given in the equation. If it is equals to 1, then time domain condition. This first equation is considered as a time domain condition for 0 ISI, and this implies that equation A assures the perfect reception in the presence of noise. Next, this equation represents the time domain condition for 0 ISI. And next one we have the frequency domain condition for the perfect reception. So next we have Nyquist criteria for distortionless baseband binary transmission. So here P delta of f will be equals to integral minus infinity to infinity summation n equals minus infinity to infinity P of ntb into delta of t minus ntb into e power minus j2 pi ft into dt. So substituting the values, we will get these equations here. Next, we have here using the equation C and equation D. In this, we are getting here the equation D here. It is the frequency domain condition for 0 ISI in the absence of noise. Next, this is the Nyquist criteria for a distortionless baseband binary transmission. Next, we have ideal solution. So although there are the choice of pulse P of t achieves economy in bandwidth in that it solves the problem of zero intersymbol interference with the minimum bandwidth possible. So for that there are two practical difficulties here. That is, it requires that the amplitude characteristics of P of f flat from minus B0 to plus B0. This is physically unreliable because of the abrupt transitions at plus or minus B0. And also the function P of t decreases at a slow rate of decay that is caused by discontinuity of P of f at plus or minus B0. So for this practical solution to overcome this, so we are using here extending the bandwidth from B0 to RB by 2 to an adjustable value between B0 and 2B0. While doing this, we permit three components in the series on the left side of the equation here. So next we have here a request criteria for distortion baseband binary transmission here. So this is P of F equation where the parameter alpha here it is called as a roll-off factor where alpha is equal to 0 and F1 is equal to B naught, and then we get a minimum bandwidth solution described earlier. Then this is the Nyquist criteria for distortionless baseband. So this is this figure here. It is an with ideal low pass filter, and this is for a low. This is a roll off factor and frequency response of this filter here. Next, we have a correlative coding. So that is adding ISI to the transmitter signal in a controlled manner. It is possible to achieve a bit rate of 2 B0 bits per second in a channel of bandwidth B0 Hz. Such schemes are called correlative coding or partial response signal schemes. Since the introduced ISI is known, its effect can be compensated at the receiver. So, and also here this correlative coding may be regarded as a practical means of achieving the theoretical maximum signaling rate of 2 B0 bits per second in a bandwidth of B0 Hz, as postulated by Nyquist using reliable and perturbable tolerant filters. This is a correlative coding, that is transmitting a uh, uh, two omega symbols with 0 ISI using the theoretical minimum bandwidth of omega hertz without infinity short filters. Correlative coding or duo-binary signaling introduces some controlled amount of ISI into the data stream rather than trying to eliminate ISI completely and duo-binary signals. So next we have correlative coding. So here in this correlative coding is introduced into transmitter signal is known. Its effect can be interrupted at the receiver in a deterministic way. Next we have duo binary signaling. So